The table below shows the relation R on a set A equals A, B, C, D, E. Find the relation R. Determine whether the relation R is reflexive, symmetric, or transitive. Determine whether R is an equivalence relation. So to solve this, let's look at our table. Wherever there is a 1, it means there is a relation between those two pairs. It's in row by column. Wherever there is a 0, there is no relation. So we can see there is a relation between A and A. A, C, AD, BB, BE, CA, CC, CD, DA, DC, DD, EB, and EE. So that is the relation. Write them down as ordered pairs. Now let's determine whether the relation is reflexive. So a relation is reflexive if for each element it relates to itself. So mathematically, for all of x being an element of A, x relates to x. So from our table, we can see that A relates to A, B relates to B, C relates to C, D relates to D, and E relates to E. So there is none left out. Let's write them down in infix notation. Therefore, our relation is reflexive if any of these elements of A were to be left out, then it wouldn't have been reflexive. Let's now test the symmetric rule. So a relation is symmetric if A relates to B, then the reverse is also true. So mathematically, a relation is symmetric if for all of x, y belonging to a set A, x relates to y, therefore y relates to x. So we can see from our relation that A relates to C, therefore C relates to A. So A relates to D, and there's D2 relating to A. B relates to E, and there is E relating to B. C relates to D, and there is D relating to C. So it means that our relation R is symmetric. So from our table, A relates to C, so there should be C relating to A, and it's true. There is C relating to A. A relates to D, so there must be D relating to A. It's true, we can find it in our relation. B relates to E, therefore E also relates to B. C relates to D, therefore D relates to C. Therefore, our relation is symmetric. For the transitive rule, if A relates to B and B relates to C, then there should be A relating to C. So mathematically, a relation is transitive if for all of x, y, z being elements of A, x relates to R and y relates to z, implies that there is a shortcut x relates to z. So from our table, A relates to C and C relates to D, so there should be A relating to D, and it's there. We have C relating to A and A relating to D. It should mean that there is C relating to D for it to be transitive. B relates to E and E relates to B. There should be B relating to B for it to be transitive, and it's true for our relation R. Therefore, R is transitive. So I didn't consider the reflexive ones because automatically they are transitive. Now back to our reflexive property. To show that a relation is reflective, you can check the main diagonal of our table. So you can see that it contains all ones, so it means that it's reflexive. So if any of them has a 0, then it's not reflexive. Now for our symmetric property too, you can look at the table and taking the main diagonal of as the line of symmetry. Whatever is at the bottom triangle is at the top triangle. So now to the last question. Determine whether R is an equivalence relation. So yes, R is an equivalence relation since R is reflexive, symmetric, and transitive.